So this will be, I think, the second day in Chapter 3 of Electronics 1, talking more about semiconductors. And I'll just review for a little bit where we got. So if we have a regular crystal lattice, something like this, if we have silicon atoms, or these orange dots, and the red lines represent two electrons bonding them, if we replace one of those electron atoms, those silicon atoms, with a pentavalent element such as arsenic that has 5 electrons in its outer shell, it can donate an electron to this crystal lattice, and that electron would be easy to move around. It'd be a free electron, and it would leave behind a fixed positive charge where it left from. Now, if that happens, we'd call that N-type. We'd made an N-type semiconductor, and that concentration of arsenic atoms would be called Nd, would be the donor doping concentration. And that would be the number of atoms we added to it per cubic centimeter. That's not quite review, that's something new, but this arsenic atom here donated an electron to the semiconductor. Donated an electron, and it didn't create a hole, right? It created a fixed positive charge that can't move from that phosphorus atom, but it donated an electron to the crystal lattice. Down here, if we substituted for one of these silicon atoms a boron atom, which has 3 electrons in its outer shell instead of the 4 of silicon, then there'd be a missing electron, and a missing electron is a hole. And we'd call that p-type. And we'd have an acceptor doping density, meaning that concentration or density, and that's in the number of atoms, again, per cubic centimeter, meaning that this p-type dopant, in this case boron, has added a hole to the semiconductor lattice, and a hole is a positively charged conducting particle, just like an electron is a negatively charged conducting particle. Now, I briefly mentioned that there's a mass action law, and that still holds. It still holds. We still have the case where the concentration of free electrons times the concentration of free holes equals the intrinsic carrier concentration. Squared, I should say. That still holds. And so then the question is, when we add these dopant atoms, what is the electron concentration? Well, it turns out that N will be basically equal to Nd, and P will basically be equal to the acceptor doping concentration. So essentially all of the dopant atoms at room temperature, all of the donor dopant atoms will create electrons, and all of the acceptor dopant atoms will create holes. Now, in order for a material to be N or p-type, we need to have either the electron concentration greater or less than the hole concentration. So if we have let me just write that better. So if N is greater than P, it's N-type. And if P is greater than N, it's P-type. We can have the case where we have both N-type dopant and P-type dopant, but to keep it easy, we'll just say that we only have Na or Nd. And so if it's N-type, let's say if we have 1e to the 15, and typical doping concentrations are so I should say, let's see, whether it's N-type or P-type, it's typically no more than about 1e to the 19 for doping concentrations. Doesn't help when I write something that's not in my notes. It works either way for acceptor or doping or donor doping concentration. The typical levels are somewhere between 1e to the 15 and 1e to the 19, something like that. Maybe a little higher, maybe a little less. Some strange things happen over about 1e to the 18. So, but let's say if we had the case where the doping concentration was 1e to the 15, by this mass action law, then we've got Nd is about the same as N, so we'd have Np is equal to Ndp is equal to Ni squared, and actually we know Ni squared, and if we know that Nd is 1e to the 15, then we can solve for P and find what P is. So it's Ni squared over Nd, which would be 1.5e to the 10 squared over 1e to the 15. And it looks like I didn't do it, but I can do it here easily. So it's 1.5e to the 10 squared divided by 1e to the 15. And we get 225,000 holes per cubic centimeter. And I usually would just say 225 per cubic centimeter is what I would usually say. But that should seem like not very many compared to, remember, silicon has 2e to the 22 atoms per cubic centimeter. So I've added just a tiny percentage of dopant, 1e to the 15, but by doing that, because of this mass action law, the concentration of holes is really, really small. We've got far more electrons now than holes. The holes are the freely moving positively charged particles, and we only have 225,000 holes per cubic centimeter, while we have 1e to the 15, so a million trillion, something like that. It's some really big number, right? 1e to the 15 electrons per cubic centimeter, and 225,000 holes per cubic centimeter, compared to, in both cases, the silicon concentration of 2 times 10 to the 22 atoms per cubic centimeter. So there's this huge change, this huge swing between having N-type material would have a huge number of electrons compared to holes, and P-type material would have a huge number of holes compared to electrons. I could do that example just the opposite, just the same way. Now, I could do it the other way. If Na is equal to, say, 1e to the 16, then N would be Ni squared over Na. And I know this sounds like I'm doing examples, I am, but I'll do more of them in the recitation. 1.5e to the 10 squared over 1e to the 16. That would equal 22,000, right? electrons per cubic centimeter. It's p-type. Up here we had n-type because the it's n-type up here because we had more electrons than holes, and now we have, if we dope it with acceptors, then we've got more holes than electrons. We only have 22,000 electrons per cubic centimeter, but we have 1 × 10^16 holes per cubic centimeter. So that's by doping we get a huge increase in in concentration, and this lowers the resistivity by many orders of magnitude. So I've got to talk about what that means. It's still much worse than metals, but the fundamental thing is that we can make a semiconductor which is almost entirely composed of free electrons, not quite, but almost entirely, or we can make it almost entirely free of electrons and make it almost full of holes, that's p-type, just by changing the doping. Now we call a majority carrier, let's see, it's better to show by example. So for n-type, in p-type, we have the donor doping density, and for p-type we have the acceptor density, that's the number per cubic centimeter. In n-type, we'll have n is greater than p, because always ni squared is equal to n times p. So we'll have n is greater than p. Well, I should say first that n is basically the same as nd. And n will be greater than p. And we say that the majority carrier for p-type is electrons, and the minority carrier is holes. That may seem like kind of a silly way to talk about it, but it's nice because it actually sort of normalizes out it doesn't really matter whether we're talking about p or n-type material. For p-type material, the electron or the hole concentration is essentially the same as the acceptor doping density concentration, and there'll be more holes than electrons, and the majority carrier will be holes. And the minority carrier is electrons. It's much easier to talk about sort of generalizations about things like that than to talk about exactly what's going on. So majority and minority carriers are often a very useful way of talking about just what is happening in a chunk of semiconductor. Now, if we put a charge on some semiconductor, we can get it to conduct electricity. So let's first draw a chunk of semiconductor. This is my cheesy three-dimensional drawing of a bar of semiconductor. And we've got some cross-sectional area. We could just look at it anywhere and we could say we've got a cross-sectional area. It's just drawing a slice through there. And if we connect a wire to this side and back to that other side and hook up a a voltage source like a battery, so we have a positive and a negative charge. We have positive on this end and negative on that end. That area might be in centimeters squared. Once we do that, and if we've got so we've got some length to this, there'll be an electric field in this direction, from positive to negative. And electrons will be attracted to this positive side, because there's a positive charge on this side, so electrons are attracted. They're pushed away from that negative charge, but holes will be attracted to that that negative side. So holes will come out this way, and electrons will go that way. And as it happened, Ben Franklin defined current going in as current going into the positive terminal, so we're stuck with that convention. It means that current flows in the opposite direction of electrons, but it flows in the same direction as holes. So if we put a charge on there, on either ends of this bar of semiconductor, at a bar of silicon, whether it's doped or not, charges will flow to the ends, and we'll have a field develop, because electric field is volts per length. So the electric field equals volts per centimeter. It equals voltage per length. Volts per meter, volts per centimeter. Now, I said there'll be current flowing, and it'll be going from plus to minus. Current, amps, are coulombs per second, charge per second. That's a current. So there's an electric field, and there's a current. And we also know that these electrons, for instance, that are inside of here will be accelerated in this direction of this positive charge, and the holes that are in here will be accelerated in the direction of that negative charge. And you may be really uncomfortable with the idea of holes being moving and being accelerated. A hole is nothing but a missing electron, right? And so if we have holes flowing out, then that means we actually have electrons flowing in, which is the direction of electrons. Electrons are flowing this way, which is the opposite of the current. So if we have electrons flowing in, that means holes are coming out, and it's all consistent. It may seem just totally weird, but it's consistent. Now, electric field will keep pulling, just like, so gravity pulls on your shoes or on an apple and continuously accelerates that. An electric field will continuously accelerate these charges, and it'll give them a velocity. We call that a drift velocity. And that's related to electric field by a proportionality constant called mu. And so for electrons, we would have a drift velocity of minus mu sub n times the electric field. And for holes, we'd have a drift velocity equal of mu sub p times z. The sign just takes care of the direction that they're going, and it'll work out easier if we use a negative for electrons. Mu is this proportionality constant that we use to fix the units between drift velocity and field. So velocity equals mobility times field, or mu sub n times e for electrons, and mu sub p times e for holes, and mu is a proportionality constant. And to make those units work out, so we have velocity over electric field, which is centimeters per second, over field, which is volts per centimeter. So we get these goofy units of centimeter squared over volt seconds. I don't know what those mean. They're weird, right? I can't say what they mean, but I can say that that's a mobility. And I can also say that the mobility of electrons in silicon at room temperature and kind of typical situation is about 1350 centimeters squared per volt second. All by itself, that doesn't really help you much. But if you can compare it to hole, holes are something like, say, 480 centimeters squared per volt second. So holes are much slower than electrons in silicon. We can say that because drift velocity is mobility times field. So for the same field, we have a higher mobility for electrons than holes. So the drift velocity for holes will be less than the drift velocity for electrons. Now, so let me write this. It's just more than I can write on one page, but I'd like to keep some of it in there. So mobility is in the units of centimeters squared per volt second. And field is volts per centimeter. Current is amps or coulomb per second. Let's see, what other units or other bits should I mention? Well, we have velocity, drift velocity is equal to mobility times field, whether it's electron or hole. We could put either one in, so you might have a minus sign, but basically that's what it says. And current, again, is coulombs per second. So I is equal to coulombs per second. And so then the question is, how can we get that? Well, we already have, well, let's see. What it is it's for electrons. Then we'd have the concentration of electrons times the charge on a single electron times its drift velocity. And we need to put a negative sign for the right direction. So is that really correct? Well, we have a negative times N is, so we have per cubic centimeter, we have coulombs, and we have centimeters per second. So we've got centimeters minus 3 for N is the units there, and Q is the charge on one electron, so that's the units of coulombs, and velocity is centimeters per second. So one of these centimeters is going to go away, right? We're going to have the number of coulombs per centimeter squared second, or that would be amps per centimeter squared. right? Because coulombs per second is amps, so we got amps per centimeter squared. That's the current, and that actually, we don't usually call that current I. What we actually usually call that is J for current density. And that's centimeter or amps per centimeter squared. Again, actually current density is nice because it helps us get rid of differences between different size devices. And Jn specifically would be the drift current density, I should say, of electrons. Right, and we could get the current is just multiply J times A. That would be amps instead of amps per square centimeter. Someone's knocking on my door.